Start out with the graph, but there ain't no XY axis. Just some circle shapes called nodes that are connected by some edges. Imagine each node is a pipe you want water to flow through, and the edges between nodes make a path that the water can go through. Each of these edges has a max capacity it can hold. It's the max amount of water that can go through that pipe and not explode. What you're flowing in always has to equal what you're flowing out, but make sure the flow that you're flowing is always less than the max amount. So given a pipe network, how do we find the maximum flow? We call the start the source, the end the sink, and between internal nodes, we want to find augmenting paths with a simple definition. Augmenting paths are paths from source to sink, start to destination. Here's an augmenting path that fits the given specification. Look at the values on each edge, that's where you pay close attention, because out of all the edges there's one whose capacity is least, and so that is the max amount of flow that can go through the path you see. The bottleneck value B is the so-called smallest value of this path, and we use it to update something we call the residual graph. The residual graph, GF, is a version of original graph G, but GF updates the augmenting path with its altered capacities. To get the new graph, first look at each edge on the augmenting path. If it's going left to right, just subtract B, and that's that. But also include an arrow, right to left, between the edges nodes, labeled with the value B, because you can have backward flow. A backward edge opposes the direction that flow should go. So when you go through backward edges, you're actually decreasing the flow. We'll label backward edges using squiggly lines and update them by adding to its capacity the B value we find. So now that backward edges are something that we know, after updating, there's an edge for which the capacity is 0. Go ahead and delete this edge from all existence, and now it's time for the algorithm to recommence. It should be simpler this time now that you know what is expected. Step 1, find an augmenting path in the graph that we updated. Step 2, find the bottleneck value B, that's minimum capacity. Step 3, make forward edges subtract B, and backward edges add B. Update the graph again. See how it makes a difference? You're getting rid of augmenting paths with every iteration, because soon the source will have no arrows coming out of it, and there won't be paths from source to sink in all entirety. I do all the remaining steps until I reach the end, and once I do, I know the maximum flow of all I did. It depends on keeping track of the bottleneck values I got. Adding them all up gives me the maximum flow I can allot. You can use this methodology for many operations. Matching problems in highway traffic are just some applications. From augmenting paths to updated graphs and all else you now know, you can easily use Ford-Fulkerson for calculating maximum flow.